Welcome to This Explainer. Today, we're popping the hood to uncover some absolutely fascinating hidden engineering. We're going to break down the incredibly complex split-second chain reaction required to crank a modern engine and bring it roaring to life. It's quite the ride, so let's get into it.
Okay, let's dive into this. What actually happens when you turn the key or, press the start button in your car? It seems completely instantaneous to us sitting there in the driver's seat, right? But in that tiny fraction of a second, you're actually triggering a massive mechanical and electrical symphony. It's this amazing sequence of events, and it's all centered around one incredibly clever piece of machinery: the pre-engaged starter motor.
Section 1. The ignition chain reaction.
Before we can spin anything mechanically, we hit our first major engineering roadblock, which is getting power from the battery to a high-voltage starter motor safely. See, wiring the battery directly to the starter sounds super simple, right? But the ignition switch on your dashboard only handles a very low electrical current. It's just a delicate little switch. The starter motor, on the other hand, demands a massive surge of heavy current. If you wired them directly, you'd need this hilariously clunky, giant switch right on your dashboard, plus dangerously thick copper wires running through the cabin just to handle the load safely. It would be an absolute mess and totally unsafe.
Section 2. The brilliant solenoid solution.
So, to solve this massive electrical mismatch, engineers brought in a brilliant intermediary component called the solenoid. Essentially, it's an electromagnet that requires just a tiny bit of current to wake up. You can think of it as the ultimate electrical heavy lifter. Placed right between the two systems, it allows that gentle low-current turn of your key to safely command a massive electrical load, all without melting the delicate electronics inside your dash.
Here's exactly how this split-second chain reaction plays out. First, turning the ignition energizes the electromagnet inside the solenoid. Second, this really strong magnetic field forcefully pulls on a moving core, which we call a plunger, causing it to slide forward along the coil. Third, as this plunger slides to its physical limit, it slams against a contactor switch, physically bridging two thick copper terminals together. And finally, step 4, this massive physical bridge completes the heavy-duty circuit directly from your battery to the motor, spinning the rotor with some incredible force.
Section 3. Meshing with the flywheel. Now that raw electrical power is flowing safely to the motor, we have to transition that into physical movement to actually wake up the car's heavy engine. And here's the crucial point. The solenoid isn't just some fancy electrical switch. It actually has a second, highly physical job happening at the exact same time. As that magnetic plunger moves forward to complete the circuit, it also physically pushes a small gear, called a pinion, outward to lock into the massive teeth of the engine's flywheel. The timing is just brilliant here. It does this physical sliding before the motor gets the juice to start spinning.
But think about it for a second. What happens if the teeth of that tiny sliding gear and the massive resting flywheel don't align perfectly? Well, they just smash into each other, right? And this brilliantly illustrates the elegance of mechanical engineering. Enter the helical spline. This grooved mechanism forces the sliding pinion to rotate just slightly on its axis as it moves forward. This subtle, twisting rotation ensures the pinion meshes perfectly, smoothly, and conveniently with the flywheel teeth every single time, all before that high-power electricity kicks in.
Section 4. Generating massive torque.
All right, so now we're physically connected, but we face our second major engineering problem. That tiny electric starter motor is far too weak on its own to crank a heavy, resting engine block that's literally fighting against internal friction and compression. Just picture the sheer physical size difference under the hood. How in the world can a tiny sliding gear dictate terms to a massive engine block? It's the ultimate David and Goliath scenario. It's kind of like a tiny bodybuilder trying to move a mountain. The secret to pulling this off relies entirely on mechanical force and multiplying torque through gear ratios.
The very first step in leveling this playing field is the initial gear ratio between the massive flywheel and that tiny pinion gear we just engaged. Generally, this ratio sits anywhere from 15:1 to 20:1. This massive size difference acts like a huge lever. It basically means for every 15 to 20 revolutions of the tiny starter gear, the massive engine turns exactly once. This dynamic setup provides a really high initial burst of torque just to get things moving.
But here's where the physical stakes get even higher. Because despite this massive mechanical advantage of the flywheel, a compact electric motor of this size still doesn't have enough muscle. Even a 20:1 gear reduction is completely insufficient to crank a cold, heavy engine on its own. The motor is absolutely going to need more help before it literally burns itself out trying